Today, let's dive into one of the most fascinating concepts in both physics and philosophy: absolute space and time. Now imagine you're floating in an endless void. No stars, no planets, just nothing. This is the realm where the idea of absolute space comes into play. Absolute space, as proposed by Sir Isaac Newton, is the notion that space exists as a vast, unchanging stage where all events unfold. It's like an invisible grid that gives each object a precise location, independent of everything else. On the flip side, we have absolute time. According to Newton, time flows uniformly, like a river that never speeds up or slows down. It's the same for everyone, everywhere, no matter what. This idea is really neat because it gives us a universal clock ticking away the seconds, minutes, and hours in perfect harmony. But hold on, this isn't the end of the story. Along comes Albert Einstein, who throws a bit of a wrench into Newton's clockwork universe. With his theory of special relativity, Einstein shows us that space and time aren't as absolute as Newton thought. Instead, they're woven together in a fabric called spacetime. And guess what? This fabric can bend and stretch. This means time isn't absolute but relative depending on your frame of reference. Philosophers had a field day with this. They began to question, if space and time aren't absolute, does that mean reality is subjective? Are our experiences of the universe just perceptions? Some argue that Newtonian absolute space and time provide a comforting anchor in an ever-changing world, while others embrace Einstein's fluid spacetime for its elegant complexity. However, special relativity revolutionized this notion by intertwining the two into a single continuum known as spacetime. In the realm of special relativity, the ideas of absolute time and absolute space were rendered obsolete. Instead, we now understand that the fabric of spacetime can be curved, leading to a dynamic and interconnected universe. One of the most intriguing concepts introduced by special relativity is that of absolute simultaneity. Previously, it was assumed that events occurring at different locations could be agreed upon as simultaneous by all observers. However, Einstein's theory discarded this notion, introducing the relativity of simultaneity. In simple terms, an event that appears simultaneous with another event in one frame of reference might be perceived as occurring in the past or future in another frame of reference. According to Newton, absolute time and space respectively are independent aspects of objective reality. Absolute, true and mathematical time of itself and from its own nature flows equably without regard to anything external, and by another name is called duration. Relative, apparent, and common time is some sensible and external, whether accurate or unequable measure of duration by the means of motion, which is commonly used instead of true time. According to Newton, absolute time exists independently of any perceiver, and progresses at a consistent pace throughout the universe. Unlike relative time, Newton believed absolute time was imperceptible and could only be understood mathematically. Humans, on the other hand, are only capable of perceiving relative time, which is a measurement of perceivable objects in motion, like the moon or sun. From these movements, we infer the passage of time. Absolute space in its own nature, without regard to anything external, remains always similar and immovable. Relative space is some movable dimension or measure of the absolute spaces, which our senses determine by its position to bodies, and which is vulgarly taken for immovable space. These notions imply that absolute space and time do not depend upon physical events, but are a backdrop or stage setting within which physical phenomena occur. Thus, every object has an absolute state of motion relative to absolute space, so that an object must be either in a state of absolute rest or moving at some absolute speed. Historically, there have been differing views on the concept of absolute space and time. Gottfried Leibniz was of the opinion that space made no sense except as the relative location of bodies, and time made no sense except as the relative movement of bodies. George Berkeley suggested that, lacking any point of reference, a sphere in an otherwise empty universe could not be conceived to rotate, and a pair of spheres could be conceived to rotate relative to one another, but not to rotate about their center of gravity, an example later raised by Albert Einstein in his development of general relativity. A more recent form of these objections was made by Ernst Mach. Mach's principle proposes that mechanics is entirely about relative motion of bodies and, in particular, mass is an expression of such relative motion. So, for example, a single particle in a universe with no other bodies would have zero mass. According to Mach, Newton's examples simply illustrate relative rotation of spheres and the bulk of the universe, when, accordingly, we say that a body preserves unchanged its direction and velocity in space, Our assertion is nothing more or less than an abbreviated reference to the entire universe, said by Mach. The laws of physics transform from one inertial frame to another according to Galilean relativity. The existence of absolute space contradicts the internal logic of classical mechanics, since, according to Galilean principle of relativity, none of the inertial frames can be singled out. Absolute space does not explain inertial forces since they are related to acceleration with respect to any one of the inertial frames. Absolute space acts on physical objects by inducing their resistance to acceleration, but it cannot be acted upon. Newton himself recognized the role of inertial frames. The motions of bodies included in a given space are the same among themselves, whether that space is at rest or moves uniformly forward in a straight line. As a practical matter, inertial frames often are taken as frames moving uniformly with respect to the fixed stars. Einstein's take on the ether, especially in his later papers, introduces a unique perspective that aligns with his broader theories of relativity. He identified the term ether with the properties of space, a terminology that, while not widely used, offers a significant insight into the fabric of our universe. Einstein stated that in general relativity, the ether is not absolute anymore. This is because the geodesic, and therefore the structure of spacetime, depends on the presence of matter. To deny the ether in Einstein's view is to assume that empty space has no physical qualities whatsoever. He argued that the fundamental facts of mechanics do not harmonize with this view. To illustrate this, Einstein referenced Newton's concept of absolute space. Newton objectivized space to account for rotation and acceleration as real phenomena. For Newton, absolute space, or what he might as well have called ether, was essential to enable acceleration or rotation to be considered real. Einstein extended this idea by suggesting that the ether, in the context of relativity, is four-dimensional. This is because simultaneous states at different locations in the ether could no longer be defined in an absolute sense. The theory of relativity resolved this by establishing the behavior of electrically neutral point masses via the law of the geodetic line. This law unified inertial and gravitational effects, attaching characteristics to the ether that vary locally based on the distribution of mass and energy. Thus, the ether in general relativity differs significantly from that in classical mechanics and special relativity. It is not absolute but is instead determined by the presence of ponderable matter. Special relativity had already eliminated the concept of absolute time, although thinkers like Gödel have speculated that absolute time might hold validity under certain forms of general relativity. General relativity takes this a step further by diminishing the scope of absolute space and time through the concept of geodesics. Geodesics, the paths that objects follow under the influence of gravity alone. Interestingly, there appears to be a form of absolute space in relation to distant stars. This is because local geodesics eventually channel information from these stars, creating a sort of cosmic reference frame. However, invoking absolute space is unnecessary for describing the physics of any system. The local geodesics are sufficient to map out its space-time fabric. As we draw our exploration to a close, from the early philosophical musings of absolute space and time, to the Einstein's theories of relativity, Newton's ideas laid a foundation, but it was Einstein who shattered the rigid constructs of absolutes, opening our minds to a more fluid and interconnected universe. Through the lens of general relativity, we have bridged the macro and micro realms, revealing how local geodesics and cosmic phenomena are intertwined within the curvature of spacetime.